Okay, now in core 1 we would be able to find the equation of the line y equals if I was told that the curve was going through the point P, 1, 8. Okay, so the method would be integrating this, so I'd have y is equal to 4x cubed over 3 plus x plus a constant c, sub in the point 1, 8, and that would give me c, so I'd have 8 is equal to 4/3 plus 1 plus c, so c would be 8, take away 4/3, take away 1, so 17/3. So y is equal to 4x cubed over 3 plus x plus 17 over 3. And then if I wanted to work out what the point Q was, which was 1.1, so a little bit away from P, so quite close, I could just substitute 1.1 into this. 4 times 1.1 cubed divided by 3 plus 1.1 plus 17 over 3. And that gets me 3,203 over 375. It gives me the exact answer, which is about 8.54. Okay? So this is a core 1 method, right, that I can use to work out a point that is very close to P and work out the coordinate, the y coordinate. Okay? However, if we were looking at the square root of 4x squared plus 1, and I said that P 1, 8 lied on the curve, and I wanted to find the y coordinate of Q, then we hit a problem, because we need to be able to integrate the square root of 4x squared plus 1. We are not currently at a stage where we can analytically integrate that. And by analytically I mean come up with the algebraic solution of integrating this. It's too complicated for us. So what we can do is try to find a numerical equivalent. Or, well, not an equivalent, but a numerical approximation to it. And this is where Euler's step-by-step method comes in. So it's unlike our previous numerical methods where we've been trying to find the root of an equation. This is doing something slightly different. So what we're going to do is, if we looked at the curve in question, and here's my point P, for example, there it is, 1, 8, and I say here's Q, which is at 1.1 y, okay, then if I looked at the right angled triangle between those 2 points, then maybe if they are close enough, I could approximate the position of Q. So let's say that this length is delta x. So delta is a letter, a Greek letter that we use in mathematics often to mean a small amount. So a small amount of x and a small amount of y, delta y. Then what we would find is that if I looked at the gradient of the chord between P and Q, then that would be delta y over delta x. And if P and Q are quite close together, then that gradient of the chord will be approximately equal to the derivative. So dy by dx will be approximately equal to delta y, let's write it around the other way, delta y over delta x will be approximately equal to dy by dx. So if I multiply both sides by the delta x, I can say that delta y is approximately dy by dx times delta x. Okay. Now, let's put this into practice then. I would therefore be saying that y would be equal to 8 plus that delta y. Okay? Or is approximately equal to I'll put approximately equal to 8 plus delta y. So 8 plus dy by dx times delta x. Now that dy by dx is the gradient that's evaluated at that x coordinate, okay? So it will be approximately 8 plus dy by dx times delta x. And dy by dx is evaluated at p, okay? So when x is 1. So I can approximate y by saying, right, that's 8 plus dy by dx when x is 1, so I get 4 plus 1, so root 5, times by delta x. Now delta x in this case is just 0.1, the x coordinate distance between 1 and 1.1. So I would get 8 plus root 5 times 0.1, which is 8.2236 to 4 decimal places. Okay, so that would be an estimate, an approximation for y. So that would be my coordinate. Okay, so if we want to generalize this, this is what Euler's step-by-step method would be saying. So if dy by dx was some function of x, I just want to make sure I get this written down correctly, then my value of y, my new value of y, okay, my second coordinate value of y, will be yn, okay, my first value of y, plus that delta x, okay, which I'm going to label as h, times by dy by dx, so f of x of n, evaluated at xn. So this is my formula where h is the step length, okay? So we say that xn plus 1 is equal to xn plus h. H is the step length that I choose. So the step length could be really anything, but obviously the smaller the step length, the more accurate this is going to be. So I'm going to show you an example of how this works using the formula in the next video.